So, welcome to the lecture on transient response analysis. In this lecture, we will discuss about first order system. So, we studied the transfer function and we discussed earlier that the highest power of s in the denominator of the transfer function decides the type of the system or order of the system. So, for example, if my system is, if the transfer function is so here the highest power of s is 2, so this is a second order system, and if it is s plus 2 upon s plus 5, it is 1, so this is first order system. If we have so here is 4, so it is fourth order system. So we can, from seeing this transfer function, we can understand that what is the order of this system. So when we say first order system, it means that in the denominator the highest power of s should be 1. So this is a first order system. So let's take a first order system. So here Gs equal to a upon s plus a. This is a general first order system. Here we can take also some, not a but k or b, some other value, but it will only affect the amplitude that will result in the forced and transient response. So let's find the pole. So here s plus a equal to 0, and so s equal to minus a. So this is a pole of this first order system, and if we plot it on the s plane, let's say here this is minus a and this is a pole, so we have to cross, represent as a cross. So we represent the pole of a first order system, and this is S plane. Now if this system is subjected to some unit step input, so Cs equal to Rs into Gs. So Rs is 1 by S into Gs is a upon s plus a. So we can solve this as a upon s plus b upon s plus a. So here a plus b s plus a into a upon s plus a. Now if we compare this and this, we will get a plus b equal to 0 because there is no any s term, and a equal to a into a equal to a, so this means a equal to 1. and from here we get b equal to minus a, that is minus 1. So we can write here Cs equal to 1 upon s minus 1 upon s plus a. Now we take the inverse Laplace transform of this. So here we get Ct equal to 1 minus, here e power minus at. In this part, this is forced and this part is natural response. So the complete response comprise forced and natural response. Now let's take at t equal to 1 by a, what happens? When we take t equal to 1 by a, so Ct equal to 1 minus e power minus a into 1 by a, that is 1. So here we can write 1 minus e power minus 1 is 0.37. So this is 0.63. So we see that if this response Ct is equal to 0.63 when we have t equal to 1 by a, and this 1 by a is called the time constant. So here the time constant of a step response. So time constant is defined for if the step response of the first order system, step response rise to 63% of its final value. So here the response is 63% of the final value, and that is called the time constant. So a typical response of first order system can be plotted. So this is time and this is the response Ct. So if this is 1, the input, and here we have this response. So at t equal to 1 by a, so this is, let's say this is 0.5, this is 0.6, 0.7, 0.8 and 0.9, and similarly here we can point 1, 2, 3, 4. So 0.63 will come something here, and this is 1 by a, because at t equal to 1 by a we are getting 0.63, this response as 0.63, and this we define as time constant. Now how can we find the value of time constant? So let's take dct by dt equal to 0. So if we take dct by dt equal to 0, what we are getting? We are getting 0 because this is constant term minus a into e power minus at. So, at t equal to 0, dct by dt. So, this is the slope of this response. dct by dt is showing the slope of this response ct. So, at t equal to 0, we are getting as a. So, dct by dt we are getting equal to a. So, here we have the slope of this response at t equal to 0. So, this is t equal to 0, and here this slope, the slope will give us the value of a. So, we can see that initial slope equal to 1 upon time constant. Because this is 1 upon time constant 1 by Tc, this is equal to Tc. So, when we talk about the characteristic of a transient response of first order system or performance specification of a transient response of first order system, time constant could be one performance specification. Why? Because it shows the initial slope of the response. It means it shows the speed of the response against a step input. So, when we are in an elevator and we saw that elevator's speed of is one parameter, how fast it the response starts. So, if the slope, so this is the slope, this slope could be changed. So, here time constant will change. So, this shows the slope or speed of the response. There are some other parameters. So, here in this diagram we can see the same plot that I have plotted. We can see here this response of a step input, and at one time constant the response reaches to 63% of its final value. And so, time constant is considered as one of the transient response specification for a first order system. Now, here are two other terms Tr and Ts. So, another transient response specifications can be rise time and settling time, in addition to the time constant. So, rise time is defined as the time when the response goes from 0.1 to 0.9 of its final value. So, when the response grows and reaches, so this is 0.1 and here is 0.9. So, this time when the response grows from 10% to 90%, this is called the rise time Tr. And we can see in this diagram also, here we have the rise time Tr from 0.1 when response is at 0.1 and then it reaches to 0.9, and this is the rise time. So, rise time is a difference between the two times from 10% to 90%. Now, another one is settling time. So, settling time means the time when the response reaches and stays within 2% of its final value. So, that is settling time. So, when the response reaches to 98% and stays between 2% of its final value. So, that is the settling time. So, here we see that from 0 we start, and let us say at 4 time constant this response reaches to 0.98 and stays within 2% of its final value. So, this is the settling time. So, we see that time constant, rise time and settling time, these are the 3 transient response specifications of a first order system, and uh, uh, we can uh, we can characterize the first order system from the response and by calculating these times of the response. Now, in case of first order system, we see that there is no any overshoot. So, the first order system is characterized with also with absence of overshoot. So, this value, this final value, the response doesn't overshoot, doesn't go above this value. It is always below this final value or input or steady state value. So, the first order system is characterized with the absence of overshoot in the response. Now, we have one more point that we want to discuss, that suppose we have a response of a first order system from some experiment, and from that response we want to make the transfer function of that system. So, how can we do? So, how can we make the transfer function of a system by the response of the system? So, let us discuss. So, let us assume first that we have a general transfer function of first order, that is Gs equal to k upon s plus a. And we have this step input Rs, that is equal to 1 by s, and this is Cs. So, here Cs equal to 1 by s into k by s plus a. This is most general transfer function of a first order system. So, this we can write k by a upon s plus so here we have a by s plus b by s plus a. So, we can write a s plus a plus b s by s s plus a. So, a plus b s plus a by s s plus a. So, here a plus b equal to 0 and a equal to k. So, we find here a equal to k by a and b equal to minus a, that is equal to minus k by a. So, here a equal to k by a upon s minus k by a upon s plus a. So, when we can have Ct equal to k by a minus k by a e power minus at. So, if we want to make the transfer function of this first order system, we need to know k and a from the response, and this is the response. So suppose if we have here some response, first order response, from this response, by comparing this equation to the response, we have to find the k and a values. So we know that the time constant, that is 1 by a, we can find from the initial slope. At t equal to 0, we calculate the slope, and from the steady state value, that is the we can connect with the forced part of the response. So from these two we can find k and a. So let's take one example. So let's take that this is 0, here it is 0.72, this is a particular response 0.8, so let's see here, we have to find the transfer function from the response of a first order system, and this is an response, this is a response, you can see time varying from 0.1 to 0.8 seconds, and the response is varying from 0 to here 0.72, the steady state value. So from this we have to find the, we have to measure. So 0.72 is the steady state value or final value. So 0.72 is the final value, and time constant we want to find. So time constant is the time when the response reaches to 63% of the final value. So the 63% of the final value so 63% of the final value we can find. So we can see here so it is about 0.45. So when we have something about 0.45 and here we have some time, so the time about this 0.45 will be the time constant, because 63% value will be of the final value, that is so from here we will take the time at which this value is reached for this response, and that is the time constant. So we get that Tc equal to 0.13 second, because as this value, this we are getting this value. So this is a time constant. So to get the A is 1 upon time constant, because A is the initial slope of this response curve. So that is 1 by time constant, 1 by 0.13, and we can get 1 by 0.13 is 7.7. Now we have got one parameter of this transfer function A. Now we have to get k. So k by A is the forced response value, and that is equal to 0.72. So k by A equal to 0.72. So k is 0.72 into A, that is 7.7, and when we multiply this we can get 5.54. So the transfer function Gs we can write here k is 5.54 upon S plus A, so A is 7.7. So we saw that the first order systems, they have the transfer function, and in the denominator of the transfer function the highest power is of S is 1. So that's this is the how we can identify the first order system from the transfer function. Now come to the response. So we see that the first order system, they don't have any overshoot, and their response is exponentially growing or exponentially decaying, as the case may be. So when it is exponentially growing to the input or step value, when the response reaches to 63% of the final value, that is called the time constant, and the rise time is the time when the response reaches from 10% to 90% of the final value. Whereas the third transient response characteristic or specification is the settling time, when the response reaches and stays within 2% of the final value. So that is the settling time. So now we stop here. So thank you for this lecture. See you in the next lecture.